so capacitors, it's kind of like the application of the idea of electric fields from level 2 physics into level 3 physics and into something we can put into our circuits and is actually going to be useful. So capacitors are in absolutely everything you buy off the shelf. It's going to have capacitors in it. It's got electronics, it's got capacitors. So when we think about a capacitor, when we're thinking in our head what a capacitor is, the most simple way of thinking about it is two metal plates separated by an insulator. It could be air. So the simplest capacitor would be two metal plates that are brought close together, but not so close that they're touching, but close enough that they're really, really close. And so, initially, these capacitor plates are going to be uncharged. That doesn't mean there's no charge on them. If something's uncharged or neutral, it just means there's like an equal number of positives as what there are negatives. Something like that. So an uncharged capacitor doesn't mean there's no charge, it just means that we've got neutral charge, we've got balanced numbers of positives and negatives. And so we've got our wee power pack sitting down here. And so when we close the switch, that power pack's going to exert a force on the negative charge. It's going to move the negative charge. It's going to cause electrons to flow. Yeah, so what it means is the electrons are going to flow that way.
First try.
Okay, so the electrons flow around this way. Sorry, so that means that we're going to take some away from there, and then we're going to have a whole lot more showing up on that side of the capacitor. So that's really complicated to look at, but what we can do to simplify things is we can cancel off all the ones that double up. Something like that, ending up with a capacitor that's got a whole lot of plus on one side, all the pluses that have been left behind, and on the other side, all of the electrons that have been pumped around the circuit by the power pack. And so, how long does that current keep flowing for? Well, it keeps flowing until the electric field that's set up between these plates here, the current keeps flowing until the voltage of that electric field is equal to the voltage of the power pack. Once you've got an equal voltage here and here, no more current can flow because we've got a Kirchhoff's voltage loop law. If we add up around that circuit, we end up with a plus voltage and a minus voltage, or a minus voltage and a plus voltage. Either way, they're going to cancel out. So whichever way we draw Kirchhoff's voltage loop law, we're going to have voltage that sum to zero. And so the voltage of our capacitor will be equal to the voltage of the supply. And so what we're interested in when we're looking at a capacitor is how much charge can we fit on this thing? Like a really good capacitor can fit a whole lot of charge, but a capacitor that's not as good might fit less charge on it. And so we can measure the amount of charge that's on the capacitor. We're going to define this new idea of capacitance. Because we haven't used anything that's got capital C in it yet, we're going to use capital C for capacitance. And so capacitance is equal to how much charge you get per voltage, or much more commonly, Q equals CV. So this is the definition of capacitance, how much charge we can fit per voltage, but much more usefully when we're doing calculations here, we'll see capacitance is measured in farads. Symbol F. Except a farad is absolutely enormous. You can buy farad capacitors, but normally the capacitors we're using in circuits are picofarads or nanofarads or microfarads. So a farad is an absolutely enormous capacitance. And so the balance when we're building these capacitors is the closer together we make these plates, the more charge we can fit on, because if you think about it, if we bring those plates closer together, all these little minuses here are closer to the pluses, and they're feeling that attractive pull of the pluses, and that's allowing us to pull more charge onto those plates. And in fact, it's doing the same the other way. It's holding more positives on the plates. So the closer that we bring those two plates together, the more the capacitance is, the higher the amount of charge we can squeeze onto those plates. But the problem is, the thinner we make that insulator in between the two plates, the lower voltage it can withstand. So we have this problem of the greater we make the capacitance, the lower tolerance we've got for voltage. So if we make a capacitor that's got a really high capacitance, we can only have a tiny voltage on it, or we can have one that's got a tiny capacitance but can take quite a lot of voltage. But the key, what we would like, is to be able to have both lots of charge and lots of voltage. That's really, really hard to achieve. It's a bucket for charge. How do we use it in a circuit? It's the same as how you use a bucket. Like you fill it up with charge, and then you take it and put it somewhere you want it. You go and fill it up again. And the more charge you put in there, the longer it takes to fill. A big bucket takes a long time to fill. A small bucket's really fast to fill. Capacitor is a bucket for charge.